Thank you very much. Today we are talking about PF-Ring, that is a library that we have developed for accelerating packet processing. And the idea here is to describe what we do at NTOP, just to position our work, introduce you to the library, and to see what type of work we have done to accelerate packet capture and packet processing into Suricata. Then some real-life scenarios. Why packet capture? Because this is the first ingredient you need in order to run Suricata. It is not the main one. Okay, you have seen the presentation about pattern matching. Packet processing is the second part, but we believe that it is important to give you an idea of what we have in mind, and what we had in mind when we started the development of PF-Ring years ago. But before starting, I want to tell you a little bit about NTOP. We are a small company based in Italy and Switzerland. We develop mostly open source software. We started in 1998 with the original NTOP, from which the name. That is a network monitoring application, web-based network monitoring application. The idea was to allow people to see what was happening on the network through a web code. 1998 is a long time ago, so it means that the web was pretty new at the time. And we are still interested in traffic monitoring. Today we have a new generation called NTOP NG. So traffic monitoring was our need. In order to accelerate packet processing in network monitoring, we had to start playing with network adapters to understand the kernel mechanics, to learn how to improve things down into the kernel. And this is where PF-Ring started. So PF-Ring was started in 2003 just to accelerate packet processing for our own needs. Over time, we have realized that it was probably a good idea to try to make it more generic, because other applications that need a packet feed could be accelerated. So today, in this problem domain, we accelerate Suricata, Snort, and Grow. But our scope is not limited to security, IDS, and IPS. But again, we are coming from network monitoring, so this is our place. What is our approach? We want to be able to operate at line rate any packet size. Here I heard many times talking about gigabit. Gigabit does not say too much to me, because gigabit means volume. Here we are talking about packets. The cost of processing is per packet, not just per volume. So it is very important to talk about packet size when we talk about speed. Similar to the previous presentation, we want to leverage on modern multi-core NUMA systems, mostly Intel-based, not limited to Intel, but mostly Intel-based. We try to operate as fast as possible on commodity hardware. So you go in a shop, you buy a system, and that's it. Today is probably not a news anymore, but years ago when we started, this was not the case. There were many different types of systems. So we don't like vendor locks. We like open source. Even though open source for many people means free, doesn't mean that they want to look at the code. But for us, open source means that also we can accept contributions from other people to integrate it and to make the system better. Let's start with PF-Ring. So the story started in 2003 when I was playing with packets, and everybody was trying to accelerate the packet processing, purchasing a costly NDACE adapter. It was not an option for us because it was far too expensive. So we have said, okay, I understand that this is a good solution, but for people that can afford it, but is it possible that nobody has ever thought about doing the same using commodity hardware? Probably not achieving the same speed, but at least trying to close the gap with this type of network adapters. So we started in 2003. The word PF-Ring was coming from the name of the kernel, okay? Packet filter underscore ring, because it was a circular buffer. Over time, we have decided to go a bit closer to the FPGA-based paradigm, where they create big chunk of memory where packets are put in zero copy. Why? Because the network adapter could be reprogrammed so that the packet is moved from the wire to the memory area without any assistance from the kernel. Okay? So this allows us to operate at line speed, initially at 1G, then 10G. In 2013, we have decided to start over and to create one single API that is able to operate in zero copy. Zero copy does not mean that we are moving packet in zero copy from the network adapter to the application. This is part one. It's compulsory. Everybody must do that. Period. Zero copy for us means that once we have the packet inside the application, we can process the packet, for instance, out of order. So in case you have fragments, you can wait for fragments to arrive instead of having a mem copy. You can ship packets to a VM for another application, or we'll show you a demonstration later in the presentation. All in zero copy. Okay? So zero copy is much more than capturing packet in zero copy. Today, mem copy is pretty cheap. Okay? So saying I'm working zero copy does not mean much because the overhead you are adding is very limited. It's much more expensive to have a lock. So to lock on a semaphore than doing a mem copy. This is on modern computing. So for us, zero copy means all the way through the application, okay, balancing and everything included. So the initial version of PF-Ring was is still available, okay, but it was designed to have a ring buffer into the kernel. So the packet, one copy, so one copy to the ring buffer, and then zero copy memory map to the application. This is still available today. It is the standard way of operating. It supports all the Linux adapter. I forgot to say that PF-Ring is a Linux technology, only Linux. It's fast enough for 1G. Over 1G is kind of problematic to use. Instead, we now have another paradigm called zero copy. In this case, we have to modify the driver here. So you insert the driver into the kernel, and the system operates, as usual. Then, as soon as you open the device from the application, then we detach the ring buffer from the operating system, and you are able to access the ring directly in zero copy. As soon as you close the application, we are back to business. Okay? So it's not like DPDK where this is something special. It's on and off depending on your application. In this case, the memory here is taken from huge pages. So it means that this application can deliver to another application the packet in zero copy, simply passing the pointer. So we don't move data. As soon as the packet has been received, it means it's somewhere in the system, the packet stays, does not move. We just pass the pointer here and there. We have an API that is good news, okay? Because many times I see that people have open IOCT right to this register and so on. No, we have an API. It is independent from the vendor, and it is independent from the network speed, the network interface, and so on. The only thing that is changed when you move from one adapter to the other is the way you open the adapter. So in essence, if you develop once, you forget about your network adapter. We support many of them. I will give you a list shortly. You simply have to code once, and then we do take care of everything. So it means that you can start prototyping on your laptop and then move your code to another G adapter and run much faster. Exactly the same code. The only difference is the device name. In zero copy, so we have two types of driver. The zero copy one that is available for Intel NICs, so 11040G. That means that we are able to move packets in real zero copy to the user space, and we have one copy driver that are for non-Intel NICs or for non, let's say, Ethernet with a cable devices, with a Wi-Fi. So this means that you can use our framework not just for moving packets, but for moving data. So suppose that you have two applications that they want to speak each other. It's possible to move information from one application to the other in zero copy, or you can fan out this application. I will show you in a moment how this is possible. Simply taking advantage of a framework. So zero copy does not mean just packet. For us, a packet, it's a pointer with a length. That's it. And of course, some metadata. We have to remember from which interface came from the interface name, because eventually the application needs that. We support a pickup-based application. So we have our own version of pickup, so it means that we have a patch on top of the lib pickup so that you can take an existing application and recompile it. This is the usual way that people use our software, because they can take, for instance, existing Suricata, just use our library, and that's it. Unfortunately, pickup is not very rich in terms of functionality. Pickup is packet capture. That's it. Does not have any idea of filtering capabilities, for instance. Just to give you an idea. Modern network adapters allow to do this kind of thing, or balancing and so on. So you can use pickup, but you will have access to a subset of the information thing. We don't have complex patterns in zero copy. We just implement two, the queue and the consumer. All asynchronous, no locks, nothing, because I said a lock is much more expensive than a mem copy. So this is the point. We support KVM, so it means you can take a packet from a network adapter, move it to the hypervisor, move it to a virtual machine, do something. I will show you that in a second. And of course, Docker support is very popular these days, so you can use our software with Docker. We have native support, so it means that the software our API is inside popular tools like NIC, Suricata, Bro, and so on, in country. Okay, and an interesting thing that just to tell you in case you're interested, there's a kernel module from SysDic, the SysDic guys, that allows you to look at the operating system in terms of system code, and then we have integrated this inside our library. So it means that you can do TCP dump, and you can receive system events, okay, similar to what you do with strace, and you can save them on a pickup file. You can move them from one application to another. So this just to demonstrate the fact that for us, a packet, again, is data with a length. So AskKVM is pretty popular these days. We have decided that it was worth to look at this problem, but we have seen that we wanted to have something very simple. We wanted to have the same user experience inside the virtual machine, okay, as on a bare hardware. So it means that we don't want to see any difference. Of course, just the device name would be different, and we want to have the same speed. So it means 10G to the virtual machine without any PCIe pass-through. So it means that the virtual machine will be very dynamic. And of course, we support OpenStack, okay, because OpenStack is becoming pretty popular. But in our case, we have not decided not to accelerate OpenSwitch. That is a switch that is moving packets here and there. But instead, we wanted to focus on the virtual machine. So the idea is that we want to deliver zero copy packets to the VM, and we want to create arbitrary topologies. A typical example is the one that is depicted here. So suppose that for some reason you want to run Suricata on a VM, because you like it, because your network guys don't want to allow you to run it on the hardware. So suppose you have a VM that is doing NetFlow, so traffic processing, another VM that is doing packet to disk, another VM that is running Suricata. It is possible to create this type of pipeline, and you can use Suricata transmission zero copy, so as an IPS. You can decide to filter packets. So if you have one stage, you can take the packet and decide not to forward it to the next application, only zero copy. Forwarding means that the packet is received here, but the packet stays here. We are just passing pointers to the different applications. And there is no difference between the software running on the physical system or the software running inside KVM. Just the device name is different. Everything else will be the same. These are a couple of examples just to demonstrate that. So this is the idea, zero copy. Okay, we move data here and there. Now, why we are here today? There are many software vendors that are accelerating packet caps, HTTPDK from Intel and so on. So why we believe we are kind of unique? Okay, first of all, because we are doing this since a very long time. It's more than 12 years. So we have not started last week. And also because we support multiple vendors. Because one of the problems we see is that people are somehow not interested in supporting vendor X and vendor Y just because, sometimes NDAs, sometimes they have to learn another API, or sometimes just because they are late. So we said, in order to be interesting for the community, we have to be transparent and support multiple types of network adapters. So the user space library has been divided in several different modules. And we have modules not just for our own drivers, zero-copy drivers, but we also have drivers, modules that support different type of cards. Let's make an example. pfcount is the typical application that reads packets and counts them. Okay, you can touch the payload, but it's very simple. So we have the opposite one, pfsend, that is traffic generator. You see, we have one binary, and depending from the interface name we're going to use, we can use the vanilla Linux adapter. So it means that we go into the kernel, we have this memory ring. The case of IRQ is copying the packets. Good, 1 giga. We have zero copy, so it means the same as ZC. So it means that pfring knows that we want to open the network adapter in zero copy. Of course, we need our driver, okay, for the network adapter. Then, so the car must support it. 10G. And we can do the same with FPGA-based adapters. This is an example. This is a car from Apple Technology. That is one of the sponsors of this conference. So you see, -I, you put a different name, and that's it. At the moment, we support a few NICs, okay, beside Intel, that was always supported. But you see, this is an example, okay? We support 11041G, 100G. So it means that you can take the same application and you can run it at different speeds on top of different network adapters, simply changing the device name. The API will be the same. So you don't have to pollute your code with API X and API Y. But I want to make you a simple statement. Kelly said at the beginning of this conference, okay, don't advertise anything big, usual. Okay, this is our lifestyle since a very long time. So we want to be transparent. We want to say, okay, the user has to decide which network adapter, okay, wants to use. We want to support all of them. Our goal here is to say, our API is cross network adapters. We are not interested in deciding which one is best, but we want to tell you that if you use pfring, we take care of everything. Let's make an example. Hardware packet timestamping. This is a very good selling point for many vendors. Okay, so we have hardware timestamp. Mine is very precise, the other is much more precise, something like that. But every network vendor has a different timestamping format. If I look at Intel, even inside the Intel world, they have different timestamping formats. So your application should be doing if this, if this, if this. So this is a problem. This is a typical example where you want to take care of this type of conversion. Okay? So this means that your application can be really written once and do the rest. Of course, based on the network adapter, we'll show later some testing. You have features that others don't have. So you have in-hardware portability or in-hardware packet filtering, for instance, chip adapters don't have. But this does not mean that you have to change your code. It means that you simply code the API. In some cases, it will be emulated in software. In other cases, it will be bloody fast because it's done in hardware. That is the only difference. So what is the difference between ASIC versus FPGA-based cards? Because this is also an interesting point, okay? We would like to clarify a little bit today. Most network adapters today use an ASIC chip. So it means that it has been designed by some engineers to do specific things. There is a list of features, that's it, okay? It is very fast, but only for a specific purpose. For instance, standard network adapters, the one you find on your PC, work per packet. So it means packet by packet, the packet is delivered to the kernel, and then the kernel does something with it. If you want to go fast, this is not a very good idea because it would be better to pack packets together in a big buffer and then to ship the buffer 1 megabyte, 4 megabyte release space. But this is not very good if you want to use it for standard networking. Okay? So the ASIC chip works packet by packet. So it means that at 110G, the difference you see FPGA versus non-FPGA are limited in a way. Also, the FPGA are more optimized. But as soon as you move up 14100, you will see immediately that the idea of working packet by packet is not a good idea if you want to go fast. So the packet by packet is the first one. The second thing is memory allocation. Memory allocation usually in FPGA-based adapter is run and decided by the manufacturer. So it means that the packet are put somewhere in the system. Okay. Fine. So if you have one consumer, so if Suricata is consuming the packet with the network adapter, that is perfectly fine. But if you want to have a complex topology like the one I showed you before, where you receive the packet, you have a balance or a packet drop, let's say a traffic shaper or a selected application that is dropping packets, it is not a good idea because here you're operating zero copy. But then you have to move from the proprietary way of allocating memory to a more standard way of shipping packets to other applications. This is an important difference. Another difference is the one I said, that in modern FPGA-based adapter, they are much faster, way faster, especially at 14100, than standard network adapters because they don't work in packet mode. So they work in block mode. So they ship one block of data that contains hundreds or thousands of packets. Go ahead, please.
Sorry to interrupt you, but this is actually not correct.
Okay.
You can easily have a modern FPGA-based adapter that works packet by packet and is equally fast. It's a question of design.
This is true, but modern FPGA-based adapters that work packet by packet often are iterated through amount of memory that is moved. Move on the PCIe subsystem. Okay. Once it is in memory,
you can take it packet by packet over the PCIe subsystem as well.
This is true, but you put more pressure on the system. We have run some tests with many adapters, and we asked the engineers, and they said that this is data. We are not fabricants. I'm just reporting you, where we go. But we see differences in performance. This is what they said, and I kind of, from the software point of view, acknowledge that what they said is kind of true in the performance performance. But again, if you are an hardware guy, probably know more than us. I don't want to discuss that. So, in essence, here we have advantages and disadvantages, but mostly the bottom line is that FPGA-based adapters are great. Okay, if you use the way they have been designed. Okay, if you're able to exploit the features, not just accelerating packet capture, because this is one part of the problem. If you try to use them in ways that are not planned, let's say, okay. So, for instance, the one I showed you before with KVM packet processing in ways that are a little bit different from what the FPGA has been designed, then you might pay in terms of penalty a little bit, performance penalty a little bit. So there are advantages and disadvantages, but again, we don't want to talk about that. We want to talk about tier 3. We see advantages for vendors because if you support us, it's like supporting pickup. So it means that you have an interface that allows you to immediately accelerate existing application without you to touch existing application simply because we take care of that, or because we have created a model for the need. And we also have a way to benchmark different applications, because sometimes one of the problems is that we see that we're talking about speed, but it is different to have the same benchmark in different cards. So in this way, you can also have a way to position the software. So what does it happen if you run the software on a laptop? What does it happen if you run the software on a clustering machine with acceleration? What type of performance speed up can you expect? Here's the kind of thing. But we also see advantages for developers, because we believe we can preserve some of the developers' time simply because there's one API and we take care of the conversion. Also because we support it transparently, so you don't see many differences between one adapter to the other, just besides the interface thing. So we have one API, no NDAs, and of course we take care of the differences. Again, the hardware timestamp is one example of the kind of problem we can have when moving from one adapter to another. And the overhead we had is simply the API wrapping, so basically almost no overhead. So we don't copy packets internally. We simply give you one API for different type of network adapters. So now my colleague, Alfredo, is going to talk about the work we have done with Suricata, just to see how we can use different inside Suricata.
Yeah. So we are here for Suricata, so it's time to move on the Suricata side. So I will show you something about the state of the art of the PF-ring support in Suricata. The PF-ring packet acquisition module has not been developed by Ento, so thanks to the Suricata team, Eric and William. But we are trying to contribute for improving the PF-ring support based on latest PF-ring technologies. So in the last month, we contributed with a few patches, a few of them for enabling support for kernel bypass technologies other than the Intel zero copy based, as Luca said before. A few other pages improved the performance of the PF-ring module. We also added the IPS support some time ago. It's still under approval, but I think it will move on forward soon. I hope so. So, as I said before, we had support for non-Intel kernel bypass technologies, mostly FPGA based, such as Acme Technology, Miricom, Napatech, Telesoft will come soon. And we improved the performance. In order to measure the performance improvement, we had to decouple the packet acquisition module from the rest of the Suricata, because of course the packet processing is the real bottleneck. So we had to decouple the acquisition module. So instead of calling, let's say the capture module is getting a new packet engine from the Suricata packet pool, but instead of calling the processing function, it's just calling the release packet function in order to measure just the performance of the capture side. So this is the design we use in the test I will show you in the next slide. We ran a few tests using Suricata with a single capture thread on an E3 machine at individual line rate. After our patches, we measured performance boost of more than 50%. More than 50%. What does this mean? It does not mean that Suricata is now able to process 50 million packets per second, but this means that you now have more CPU cycles for serial processing instead of wasting time just for the packet capture T. Then we wanted to compare the PF-ring module with other modules based on the same hardware configuration. So we ran a few tests with the pickup module, the rest packet module, and the PF-ring module, both in zero configuration, in quick mode, and using the intercard in zero go. We have seen, as expected, that using the standard drivers, the number of packets per second is more or less the same, ranging from 1.5 to 2.3, I think, million packets per second. Using standard drivers, we are able to do 10 gigabit line rates of 50 million packets per second using zero copy drivers. So the limitation here is the standard kernel mechanisms used for moving packets out of the network card.
Excuse me.
Yeah.
So what's the difference between PF-ring and PF-ring quick?
Okay, PF-ring means PF-ring with standard drivers in zero configuration, which includes inside the kernel mechanism for the filtering, for clustering, etc. While the quick mode just move the packet in the compton hash and move the packet to the right queue without any clustering. So performance are important, but it's even more important to see what is the CPU utilization, because at some point we have to process packets, so we need the free CPU cycles for processing. So we run some tests with the same modules at 1 million packets per second. This is the security utilization both for the kernel, in kernel space and user space. We pick up packets with the same modules. So as you can see, as expected, with P3 zero copy, we have a very low security utilization, while we pick up in the packet, we have lots of overhead. Okay, so it was also interesting to compare the kernel bypass approaches. So we ran tests at 10 gigabits on the same machine, an E3, using Accolade card, Miricom, Navatec, and P3 in zero copy. As expected, they're all able to do 10 gig with 12.8. So not much to say here. So what's important is the CPU utilization. So we are going to see the CPU utilization at several packet rates. Okay, so we run tests at 1 million packets per second, 5 million packets per second, and 50 million packets per second. And so the blue graphs are, is the securitization using the intercard. The other graphs are FPGA-based technologies, the same in the previous slide. We didn't put the names because we want you to guess what is behind that. Thank you, Ruga. You can come back. Thank you.
Okay. So in essence, there are differences in terms of performance, not just in terms of features. But we want to talk a little bit about real-life scenarios where we have the ability of processing packets, not just in Suricata, but in other applications. So the first thing we ask ourselves is whether packet capture acceleration is a good idea. Okay, or is still a good argument, or is still the only argument, okay, we should discuss. Yeah, we think it is important, okay, but we think that that is much more than that, okay. So packet capture does not mean that everything. So it means that people in the market have changed a little bit, because in the past, okay, when we receive requests or the mailing list, people say, hey, I want to do this, I want to do that. So we're pure application, network monitoring, IDS, IPS, security, and so on. These days, they want to collapse everything into a single box. At least people try to do that. They try to have small boxes deployed here and there. They don't like to have too many boxes. Also, those boxes contain applications that are coming from different vendors, from probably different companies. The nature of the application is different. Okay, so like I said, 10G is possible with commodity hardware. Okay, sometimes the CPU left is not too much, but you know, it is definitely possible. The problem is, what about 140G? Okay, because we are now moving to 100. So today, you know, we talk mostly about 10G, but the future is 100G for sure. At 100G, okay, we have 10 times as much as 10G. And here, at the moment, the clear winners are FPGA-based adapters. There are no commodity hardware, Intel 500 euro adapter at 100G yet. So it means that there is no, we cannot do much, okay? So we have to pick one of them. But we believe that packet capture acceleration is not only the argument. If I say, okay, I want to run Suricata at 100G, good. But probably, because you're spending so much money on the card, on the box, on the line, on the SFPs, you want to do much more than that. You would like to do something a bit more sophisticated, okay, into the same box. So just to give you some ideas of what we are doing, we want to show you this. So a typical activity is, for instance, port application. So in case we have you know, a tab, so we have two lines. So what are the things we are doing here? Again, FPGA-based adapters usually do that natively in hardware, but not Intel adapters. We are able to do things like, again, this is an application that is part of PF3. You can have the source code on GitHub. We can aggregate them. Okay, we can do a fan out. We can send, you know, packets to application 1, application 2. So for instance, the first application can be a packet to disk application. So we want to write everything to disk, while at the same time we want to create, I know, network records, and we want to balance this traffic to force Suricata instances for speed and also for using all the available CPU cores, because these days you can buy machines with 12 or 14 physical cores at a very good price. So this is an example of what you can do with our demo application on top of zero coding. Another application that we can create, we can have our balancer application, and we can have Suricata running in the near future in IPS mode. So it means that you can take packet from here, send it to Suricata, and send the packet back. Okay? So this is a typical example. And here, for instance, filter packet. Because one of the things that I think is interesting to do on Suricata is to avoid Suricata spending time on traffic that is not worth. So for instance, I don't know, but many times SSH or HTTPS might be avoided, or for sure Netflix traffic or YouTube traffic. So we should try to find here a good compromise between performance and sending interesting packets to Suricata for analyzing. So one of the things we are developing at the moment is this application. So it's not yet ready, it's part of our package. So if you can download it, you can play with it, but it's not yet feature complete. It's called 100. 100 means 100 in Italian. So the idea is that we want to operate a 100G. Okay? Either with multiple 10G ports or with one 100G port. What is this application doing? So we have noticed that big companies, okay, want to generate flow records, so evidence of a certain activity on all the traffic. But they want to have, so this is network, but they want to have either saved to disk or sent to an IDS like Suricata only a subset of the traffic. For various reasons. One, because it's silly to send traffic that Suricata cannot really analyze. Two, we will use here cores for doing activities that are just exhausting your resources without producing any tangible result. So one of the things that this application is doing, it is able to have one DPI layer called NDPI, that is another open source library we have developed, that you can use to selectively say, send to Suricata DNS traffic, don't send to Suricata SSH traffic because it's encrypted, drop YouTube traffic because Suricata is not going to do much with it. And at the same time, what we envisage is to have a sort of feedback channel, because based on the alerts, it is possible, that's why I was asking yesterday about this JSON style that you send feedback back, to a sort of central box, the ability of deciding what traffic Suricata is interested in, what traffic you want to write to disk, because there are some malware installed in some of your PCs that are worth to save, but you don't want to save everything to disk, especially at 100G, because it is too challenging. At the moment, so again, these are preliminary results. With one CPU port, so one physical port, we're able to do 1488 with 500,000 flow expiring every 5 seconds, exporting NetFlow version 9, and at the same time, 2 forward packets. But the main problem that we have at the moment is the memory bandwidth, because as soon as we do NetFlow, okay, great. But if I start egressing traffic to Suricata or to a simple packet consumer, we will put pressure on the memory subsystem, so the memory bandwidth is becoming our bottleneck. Again, we are more than happy to have 6 million packets per second sent to 2 Suricata instances, but again, we would like to go faster. So anyway, the idea that I want to give you today is the following. There is much more than packet capture. Packet capture, it is interesting, but there is something more than that, especially in terms of security and evidence. So just to wrap up, the source code of TF3 is available on GitHub. It's 12 years, so we are working with it. We are able to support standard, commodity, or FPGA-based adapters. So we have contributed to Suricata, and we hope that other people that are not just on the Suricata field will use it for different type of applications. Thank you very much.
Questions? Victor.
I think on one of the slides I saw you mentioned that there
was in the PFring API a possibility to add patterns for filtering. Did I understand that correctly? It was one of the early slides, one of the. And I guess I'm wondering what kind of patterns that would be. Would that be like string patterns or some other type of?
Okay, said that I don't think I've said that, but years ago we had support for the father of hyperscan inside the PFring, but that was based on Intel Creek hardware, but it was not very exciting in terms of performance, and I agree with Intel that modern CPUs were faster than accelerating network adapters. So we have decided to remove it. But one of the things I want to do after the presentation today is to put it back. Okay, probably not inside the PFring, but inside NDPI. So we will do DPI and offer an API to application. Probably it will be a long layer, but again, we want to have the ability of. Probably is not interesting for this community, but there are people that are doing, for instance, local interception, or that are searching for a specific string, to address traffic this way, because probably need to see the beginning of the communication. But it's not there. It will be there probably. Reconsider that.
Another question. I think this is a very interesting design, especially to use NDPI to sort of filter what you would send to Suricata or whatever other application. The one thing that worries me is it's been a long time since I've looked at OpenDPI and later NDPI, but in general I found that most of these approaches were not very robust against security, in security sense. Right. So if someone tries to bypass your NDPI engine by, for example, first talk SMTP to your server and then on the same flow talk HTTP, which some servers will accept, the NDPI might actually filter something that you don't want to be filtered, and you might miss security events. So I'm kind of worried about the role of NDPI here in the security context.
Yeah, the thing that one of the open part in this application is we are developing a subset of NDPI, because NDPI is too fast for this type of application. We want to have simple filters, because most of the time people don't like BitTorrent, don't like V2. We want to reduce the amount of traffic. So, for instance, we have seen with ISPs that the 60% of the traffic today, at least in some tests, I don't want to say this is general rule, is HTTPS. Okay. So they said, okay, why don't we send this stuff, the traffic to Suricata? Okay. Another thing we want to do, especially for protocols that we can recognize immediately, such as DNS, why don't we send all the DNS traffic to one instance, all the other traffic to other instances, so that the route set can be smaller? I don't know. We are thinking about that. We are not an expert as you are, but I agree with you that these are type of problems. At the moment, we are just interested in dropping encrypted traffic. At least this is what we have been asked to do. So this is the idea.
Would there be a way for Suricata to feed back information as well?
Yeah, this is the idea.
Okay.
That's why I asked Jason as well.
Right. Okay. I guess we would want an API. That's what we discussed yesterday a bit. That shunting idea, or just be a flow bypass where Suricata would say, well, this flow is no longer interesting, so we would feed it back to the CentOS engine.
Yeah. Because here we're working per flow. This is pretty straightforward.
Yeah.
I have a question as well. I think a lot of slides that you mentioned 4D and other things with connections, but all the tests were done on 1 to 10. And also not energy. Yes, highlighters. Yeah. What the results to highlighters related to what you showed with 10 gigabytes.
But the idea here is that we want to scale. So the result as shown here, for instance, this one is one core. So the idea is that okay, we cannot scale really linearly 100%, but kind of. So as long as you have memory bandwidth in one core, so this is a slide about one core. So we want to do 10G. So this is the idea. So 40G. So we have run some tests just to give an idea with one FPGA-based adapter. So with a machine E5 2630. So we managed to process more than 100 million packets per second, 80 gigabits. So 6 cores, it was 6 cores.
I see. See where you're going.
So the idea is that you have a 12-core machine, fine. I will use 6 cores for doing all this, okay? Then I send to Suricata the information that is interesting, either because I have some blacklist or for whatever reason Suricata has decided that certain IPs or ports are more interesting. And therefore we have left 6, 8 cores to Suricata to do the job. Again, it is not a general scenario, like you said, there are drawbacks, but you know, and the same thing can scale down. So if you have 10G, more traffic. Because the point is that these guys are trying to accelerate Suricata, but on the other hand, people are putting more routes. So, you know, we have to reduce a little bit the load on the software. Again, I want to complete. So the code is on GitHub, but you can see not just PF ring, but also the example application, the balancing, dropping, and so on. Thank you very much.